Hello everyone and welcome back to Physics Talk. Today we're going to be talking about describing changing speed, basically acceleration using strobe photos and graphs. Make sure you guys take good notes, Chapter 1, Section 4. So our learning objective is really just to make sure we understand strobe photos, what that looks like for acceleration, as well as graphs for acceleration. So this is a little bit longer, I apologize, but I had to squeeze both of them in here together. Again, we're looking at analyzing and interpreting data. So I actually do some shots of actual data for this one. And we're going to look at pattern, scale, proportion, and quantity again, just like we did whenever we look at strobe photos. So a reminder from Chapter Challenge, you're expected to explain what factors affect following distance, braking distance, and total stopping distance. Well, all of that, of course, has something to do with acceleration. The acceleration of a car is one factor that affects all of them. Acceleration is a change in velocity with respect to change in time. And so we're going to look at what that motion looks like. So in terms of the strobe photos of some object moving, you can see I have a car here, two cars, one on top, one on the bottom, and of course they are moving. Can you tell who is going faster, or can you tell if someone is actually going faster afterwards? If I pay attention to then the strobe and leave the photos behind, you can see how that looks. And then last but not least, I can look at the strobe photos by putting the dots. So if we pay attention to the dots, you can see in the beginning here, these guys are not very well distanced. This guy has a nice distance here. And you look at the next one, that has a nice distance. This top one looks like it's going at a constant velocity because the spacing is equal. But the bottom one is definitely not. You can see that the spacing is increasing between them. And anytime you have an increasing spacing, that is when we have basically what we call acceleration. So in the beginning, this guy is slower. But at the end, because the spacing is so much larger, this guy is definitely moving faster. So there's the last dot for that guy. And of course, if I put my arrows on here and using the half the distance, you can see again in the beginning, this guy is at rest. But if you look at this portion here, their velocities are almost the same. This guy is getting bigger already, but this is the third dot for this one. This is only the third dot for there. So it still has more to catch up. It's finally at the fourth dot here. It's finally starting to catch up. By the fifth dot, it's long past it because that acceleration is great and its velocity is much greater than the other one. So increasing arrows definitely show acceleration. Constant arrows show constant velocity. Okay, so here we have the lab setup, making sure we have good space between ourselves and the sensor. And of course, we're just going to collect the data here and see how it looks. When looking at our data, you can see that over here is when I didn't let go yet. That's basically when it was at rest. And then we transition into this part where it's starting to move away from the motion detector. That's basically the spot where the area where the time region when it's moving down the ramp, when it's accelerating, where it's speeding up. And then in this portion over here, and this is the part that we got to make sure we're very good at, is starting to discern what data is good and what's not good data. And by looking at it, this part I don't really care about because this is the part where it fell off the ramp and made a lot of extra noise. You have to be very diligent about not copying this part of the data because this is the part of the data that doesn't really matter to us. And so you have to be very discerning in terms of which data to draw. And I would say you could draw this at rest portion and this moving down the ramp, but don't draw this portion here. Now, that means in general, when you look at that segment when it's accelerating, we get a curve that looks like this for position time graphs. Okay? And when we try to pay attention to this, you can see that what the book was asking you to do is really pay attention to slopes at certain regions of the curve. When you look at this portion here, it looks kind of like a slope like this. When you look at the slope over here, when we look at the tangent to the curve, this is what they were talking about in terms of tangent to the curve, basically the slopes of those curves. If you have a person walking up this, you can see this slope right here is pretty steep, but nothing as steep as over here when it's getting really, really tall. And so as that slope is changing, the question is what's happening there? Turns out, from last unit, we talked about how the slope of a position time graph is really the average velocity, or the speed. And so that slope is really the velocity, but if it's a straight line, that's easy. But when it's a curve, it's a little different. And so when we look at this, it turns out that yes, the slope is the velocity, but this slope is changing, which means we have a changing velocity, which means a changing velocity is defined as acceleration. And when you have an acceleration, a changing velocity is acceleration, and when you have an acceleration, that means you have a curve for a position time graph. You do not have a straight line. And so, because the slope changes on these position time graphs. Here we're going to collect another one where we're going to look at being pushed up into it. That was a bad one, so we're going to do that again. So a quick summary as to why this is actually a bad one. If you look down here, it looks like a curve should be continuing down here. But the problem is at this mark right here, when you get as close as 0.25 from the detector or 25 centimeters from the detector, it cannot read it very well. You're too close to the detector. So the idea is that you need to make sure you're not closer than a quarter or 25 centimeters away or a quarter of a meter away from the detector. Now some of you are probably wondering, how the heck do I calculate the slope of this segment over here? And remember, we can determine the velocities at given times using the data on there. All what you need to use, of course, is just your slope equation, which is rise over run, which is y2 minus y1. And the y's, of course, are all velocities. And the run is x2 minus x1, which is the time. And just subtract those times and subtract your velocities, and you should get a positive slope there. The question then becomes what does the slope tell us? It turns out that this slope tells us what acceleration is for this object. This object has a positive acceleration the whole time, which means it's accelerating away from the detector. Even though it's slowing down here, it's still accelerating away from the detector because of the positive acceleration. We'll explain more of that later. Now, in terms of a summary, here's what we have. So objects going down an incline. I just have this ball, of course, going down an incline. You can see basically a motion map for these guys, or a strobe photo showing them as they're going down. As a quick summary, in terms of what the acceleration graphs would look like, the position versus time graph. Sorry, let me get my laser pointer here. The position versus time graph. The way it's going to look, as long as it's going down, it's accelerating, and it's going away from the detector, it should just look like a nice parabola. Okay, a portion of a parabola. And again, we'll learn why it's a parabola later. But it should be a nice curve. Once you get this curve, when you analyze the tangential slopes at each of these segments, the tangential slopes, we get the velocity. And the velocity, as you saw, was a straight line. And of course, that straight line is something that we can then analyze the slope of this guy. And when we analyze the slope of this guy, it turns out to be the acceleration. Since this slope is constant, my acceleration will be constant as a horizontal line. Okay? And so, as a quick summary, make sure you draw these graphs in your notes, that the slope of position time graph gives me velocity, the slope of velocity time graph gives me acceleration, and of course, once you have the acceleration that's constant, it's basically a horizontal straight line. So that's all for today. If you have any questions, again, come to tutoring. I'm always here for you guys. All right, talk to you later. Bye.